All right, here we go. 2.3, counting partitions, which are really combinations. So we did permutations where order mattered. Now we're going to look at what are called combinations, basically where order does not matter. Okay? So what we're going to be doing is basically choosing a certain number of objects from a set, and it doesn't matter what order we put them in at all. It's like it's our subset, basically, is what we're doing. We're choosing subsets. Okay, so this combination principle here, and we've got a formula. So subset of R objects can be selected from a set of N distinct objects in that many different ways. Okay, so our formula, basically, how we write this, right, it's kind of like permutation. Okay, we say basically combination, or we say choosing, or sorry, N, we're choosing R. So we have N, we're choosing from, we're picking R objects. And that is, again, what's written there below, I'm going to write it again. Okay, N factorial, and then N minus R factorial times R factorial. So you can see it's, if you remember the permutation formula, it's just slightly different. That little bit's added in the denominator. Okay. So again, order doesn't matter, meaning if I've set A, B, C, that is the same as set C, B, A. All right, we just have those same three objects. We don't care what order they're in. All right, so go through some examples here. So if I want to find out how many combinations are there of two objects from the set A, B, C. So if I'm basically picking two from this set. So I could just count them all. I could label them all. So I've got like A, B, I have AC, and I have BC. And that's it, because if I try to do BA, that's the same as AB. All right, so I have 3 for that. All right, let's say I had to do permutations. Okay, so permutations, order matters. Actually, let me go back real quick. Combinations. So if I wanted to use the formula for this one, it would be I have 3 objects. I'm selecting or choosing 2 of them. So it would be 3 factorial over 3 minus 2 factorial times 2 factorial. Okay, which if we do that, 3 factorial is 3 times 2 times 1. 3 minus 2 factorial is 1 factorial, which is just 1. Then times 2 factorial. And then notice the 2's cancel, or 2 times 1's cancel. Yeah, 3. Okay. Permutations, all right? Remember permutations, we kind of could use a formula or just remember I'm selecting 2 objects. How many choices do I have for the first object? 3. If I pick 1, I only have 2 left for that one. So I have 6 permutations. Again, if you look at the original set, this one, so we had 3 combinations, 6 permutations, because if we flip the order, so if I flip AB, make it BA, that's a new one if we're talking permutations. All right, so it's those extra 3 that we get are just if we switch the order of each one. All right. All right, one thing to think about, think of combination as a set. When we go back to the sets, we just have our list of numbers or list of letters, whatever. Permutation is a list, all right? A list matters the order that it's in, okay? So it may help, may not. What else? Okay, so looking a little more detail with this. If we really look at this formulas here, okay, you can see the difference. Right? Our denominator has this R factorial when we talk combinations, or our order doesn't matter. Permutations doesn't have that. Okay, basically, that R factorial in the denominator right here, that's essentially accounting for what would be repeated sets, I guess. So like the BA, AB, CA, AC, it's getting rid of those extras that we don't need. essentially what's happening with that. All right. So if we want to think about which will always be bigger, permutations will always be bigger because I don't have an extra thing I'm dividing by. Right? Combinations, I'm always dividing by something extra there. Right? So an important thing to think about there. All right, so let's say I have 10 books. I can only fit 4 of them on my bookshelf, on the top row of my bookshelf. Okay, it's a very important situation here that everybody faces. So 10 books, I have to only fit 4 on the top row. Okay, how many ways can I pick the 4 books that'll go on the shelf? So I'm just picking 4. Order doesn't matter. So that means this is a combination. So I'm taking combination. I have 10 books. I'm choosing 4 of them. Okay, and this is why I'm going to give myself a little more space. So the formula is going to look like 10 factorial over 10 minus 4 factorial times 4 factorial. So 10 factorial is just 10 all the way down to 1. Then I've got 6 factorial, and then 4 factorial. Okay, so now if we look, a bunch of stuff's going to cancel. We don't have to do all of this in our heads, right? All of this, by hand. So if we notice the 6, 5, 4, 3, 2, 1 would cancel numerator and denominator. Then I have 4, 3, 2, 1. A lot of times we'll be able to cancel some of these. So like the 4 and the 2, those multiply to 8. So I can cancel those with the 8. The 3 can kind of reduce here with the 9. Divide both by 3, that takes that down to a 3. So then all I have left is 10 times 3 times 7. So 10 times 21, 210. So there's 210 ways I can pick books that will go on this top shelf. Okay, next question goes with this. Notice the wording change. How many ways can I arrange my top shelf? All right, notice the first one I was just picking them. Now we are arranging. So now we're saying order matters. So this is a permutation. So back to the last section. So draw a little picture there basically. I've got my 4 books. How many options do I have for my first book? 10. How many for my second one? 9. Then 8. And then 7. And then we multiply that out. Okay. Notice that's going to be quite a bit bigger than the 210. So again, very important the wording. Read very, very carefully. All right, so now how many ways can the chairperson of a 10-person committee select a subcommittee of 3 from our other 9 members? So it's just a committee. We're not assigning roles. If I was assigning like president, treasurer, secretary, then the order would matter. But right now I'm just picking 3 people that are going to be on my committee. So order doesn't matter. So we have combinations. All right. I have how many people to choose from. It's a 10-person committee, but I'm the chairperson, let's say. So I have 9 people to choose from. And I am choosing 3 of them. Okay. So working that out. Okay, so numerator should be 9 factorial. Denominator, I have the 9 minus 3 would be 6 factorial. 6 times 5 times the 3 factorial. Okay, I'm just using the formula there. All right, and we cancel, so those can all go. 3 can reduce with the 9. 2 can reduce with the 8. That's 3 back. Okay, then we have 3 times 4 times 7, so 84 different ways I can choose that committee. Okay, next example, set has 9 elements. How many subsets can have at most 3 elements? So at most 3, so that means 3, 2, 1, or 0 elements. Okay, so basically on this, we just need to find each one separately. So we find how many can have 3 elements. So that would be at 9 elements, choosing 3. Okay, I would figure out what that is, which we actually already figured that out. That's 84. Okay, so that's if they have 3 elements. Then we can find if they have 2 elements. Okay, at 9, 2, that ends up as 36. I'm not going to show all the work on that. Then I have 1 element, ends up as just 9. And then picking 0 elements, which would just be the empty set. So there's one way to pick the empty set. Okay. The 9, 0, why that works, so that would be 9 factorial over 0 factorial times 9 factorial. If we plug it into the formula, those cancel. That's 1. 0 factorial, if you remember from last section, is just 1, so that's why it equals 1. Okay. Once I've got this, so I have the 3, so it's 3, 2, 1, or 0. All we have to do is add all those up. Okay, add them up. That's our total number of ways. And the next slide is going to show something that basically this was partitioned, okay, into these subsets. So these are all kind of separate from each other. So that's why we add them together. Okay, so I'm going to show you on the next slide something here. So partition versus multi-stage. If a sample space is partitioned, in other words, it's broken up into parts, like the last one, we had 3 elements, 2 elements, 1 element, or 0 elements. All right, if that happens, then our outcomes we add. All right, if our experiment consists of stages, so we do one thing and then another thing, we multiply. All right. So that's something to keep in mind and think about. So if things are split up separately, we add them. If they're all kind of combined together in stages, multiply. All right. Kind of tougher example here. We have 3 cards drawn from a standard deck. How many ways can they all be the same suit? So in other words, the same suit would be all diamonds or all hearts, all clubs, all spades. Okay? So we'll get to the second question here in a minute. So same suit. So let's just say we wanted to pick all hearts. All right? So we're picking 3 cards. We have to think about how many cards do I have to choose from. All right? Order shouldn't matter here, right? It doesn't matter. We don't say anything about what order we're getting the cards in. We're just drawing the 3. So order doesn't matter. So it's combinations. How many hearts do we have in a deck? Well, there's 4 suits, 52 total cards. So 52 divided by 4. I have 13 hearts, and I'm choosing 3 of those. Okay? So that's how many ways I can select 3 hearts. If we did all diamonds, it's the exact same thing again. If we did all spades, it's the same again. All clubs, the same again. So it's this times 4. Okay, and that will give you my total ways, how many ways I can select all of the same suit. Next question asks, how many ways can they be the same rank? All right, so like the rank would mean like all kings or all 3s or all 9s, whatever. So how many ways can that happen? Well, there's 13 ranks. All right, how many cards of each rank? There's 4 cards of every rank. There's 4 hearts, or sorry, not hearts, 4 aces, 4 kings, 4 queens, 4 jacks, and so on. So there's 4 of each rank to choose from, and I'm picking 3 of those cards. But since there's 13 ranks, so let's just say this is all 2s. So then all 3s will be the same thing, right? These are all separate, so we would really add those, or we could just take, since there's 13 ranks, 13 times combination 4, 3. So those are always kind of tricky, especially first off, remembering what is a suit, what is a rank, and how many are in each one. That's first order of business there. All right, so now we have a group of 9 students, includes 6 who live in the dorms, 3 who do not. How many ways can you select a subgroup of 4? So I'm selecting 4 people. 2 are in dorms, 2 do not. All right, so order doesn't matter here. So it doesn't matter who I pick first. So we have combinations. So I'm going to do 2 separate things here. So this is kind of multi-stage. I'm going to go ahead and I'm going to select the 2 students that live in the dorms. Okay, so this is dorms. And then, so multi-stage, I'm doing this and then that. So then not dorms. So I'm going to do 2 separate things that I'm going to multiply. So for the dorms, I have 6 people that live in the dorms. We're selecting 2. For the non-dorms, I have 3 that don't live in dorms. I'm selecting 2 of those. And then we just do the calculations. Okay. Okay, similar situation. I've got 6 domestic, 8 foreign cars, and a used car lot. 7 cars chosen at random. How many ways can at most 5 be chosen? Okay, actually, sorry, it's not a similar question. I forgot about this one. So this one, we need to think about how we want to solve it. At most 5. So that means 5 domestic, or 4, or 3, or 2, or 1, or 0 domestic. That would take a long time to figure out. Okay, I could do it. All right, I could find, so 5 domestic. So I go 5 domestic. Not 5. I can start with 6 domestics. So I have 6 domestics. I can pick 5 of them, multiply that by, I have 8 foreigns. So if I pick 5 domestic, I would be picking 2 foreign. Okay, to get my 7 total. And I would have to keep going like that. So this would be for the 5 domestic, and then for 4 domestic, that would be 3 foreign. We'd have to do it all the way down. It takes forever, and then there's tons of calculations. So, think of an easier way to do that. 5, 4, 3, 2, or 1 domestic. That's obviously a lot. What we could do instead of that is do always. So all of our possible ways, not caring what type of car, minus what we don't want. So minus the complement. So the complement of the 6, 5, 4, 3, 2, 1, or 0 would be 6 domestic. So we could do all ways minus, we could go 6 domestic, 1 foreign, minus we had, this won't work, I'll explain why, but 7 domestic and 1 foreign. So I can't pick 7 domestic and 1 foreign, right? We only have 6 domestic to choose from. That's not even an option. So all we have to do on this is figure out all the possible ways, all the combinations of cars I can just pick, minus how many ways I can do 6 domestic and 1 foreign. That would be my 7 cars. So always, I have 14 total cars, and I am selecting 7. So that's all the possible combinations of cars I can pick, of 7 cars I can pick, minus what we don't want. So that's 6 domestic cars. So I have 6 domestic to choose from. I'm picking 6. And so multiply 1 foreign. So I have 8 foreign to choose from, and I pick 1. Okay. And that's how we would figure that value out. So 14, 7 takes a minute. 6, 6 is just 1. 8, 1 is just 8. So the 14, 7, whatever that is, minus 8. That's how many ways at most 5 domestic can be chosen. Those are the ones that get tricky. Those are by far the hardest ones you guys, I think, will see in this section, along with then deciding is it combination or permutation. So if you have questions on this one, be sure to ask me about it in class, and I can go over it again or do a similar one to it. All right, so that's it. Section 2.3. One more section to go. After this, section 2.4, you can see it's computing probabilities of equally likely outcomes. So let me know what questions you have.